So in this talk, I want to tell you about some results on the two systole of what I will call stretched positive scalar curvature matrix on the manifold S2 times S2. So the study of positive scalar curvature matrix is a huge topic, but it's unlike positive Ricci curvature or positive sectional curvature. It's not clear how one can use the scalar curvature to control metric invariance in a quantitative way. Here we will show in this specific case of positive scalar curvature matrix on S2 times S2 how one can control some metric invariant, namely the two systole and what we call the stretch on positive scalar curvature matrix on S2 times S2. So first I will give an outline of the talk. So first I will give a brief review of what systoles are. Then I will present some known facts about scalar curvature and how they can interact with higher systoles. So positive scalar curvature and higher systoles. Then I will present some metric inequalities by Gromov and Zhu, which will be very important in our proof. So metric inequalities in positive scalar curvature. So by Gromov and Zhu. Then I will give a proof of the main theorem, which I will have stated in the second section. So this will be the proof of what I will call the stretch systole inequality. And in the final section, I will briefly describe what open problems are, and there are many in that area. So first we will give a brief review of what I know about systoles, which isn't my first field of expertise, so I might forget some stuff, but this is the really basics. So first, let's give a definition of what is usually meant when one talks about systole. So the systole of a Riemannian manifold, Mn G, is equal to the following quantity. So this is the infimum over all non-contractible loops in my manifold M. So by this I mean this is not 0 as an element of the pi1 of M of the length with respect to the Riemannian metric G of gamma. Looking at this picture, what one can see is that so there are a number of closed geodesics and even stable ones. For instance, there is one here. There's one also here. But this one is contractible, so it is not the systole, its length at least. While this one is, so the systole would be here for this Riemannian torus. So this was studied back in 1949 by Loevner, which we will quote the result soon. But the term systole was coined by Berger, actually, by Marcel Berger. So, what can we say about systoles? So, usually the goal in this topic is to get a universal bound on the systole of any Riemannian metric on M. So this would be called systolic inequality. So, as I said, Loevner was the first to prove one in an unpublished paper in 1949. And it says the following thing. So the systole of any Riemannian metric on the torus is, so if you square it to get something which has the dimension of an area, is less or equal than 2 over square root of 3 times the area of our torus. So, and this is a sharp inequality. The equality is achieved for the flat torus coming from an equilateral lattice. So there was a lot of activities, or there was some activities afterwards on that. So namely, Pou in 52 got a sharp inequality for RP2. So Bavard in the 80s also got a sharp inequality for the Klein bottle, and then in higher genus there have been non-sharp inequalities. There were first some by Akola and Blatter, but the constant was really not great in the sense that it depended in the genus in the wrong way. Then there was one by Hebda, which had a genus independent constant, and then there were several by Gromov in the 80s. Both Hebda and Gromov were in the 80s, which had genus dependent. So Gromov had a genus dependent inequality, but where the constant improved with the genus. And also at the same time, Gromov showed that there can be non-sharp systolic inequalities in higher dimension for a huge class of manifolds. So when he got this theorem in at the beginning of the 80s, and it says the following. So for any dimension n, there exists a positive constant Cn such that if I take the systole of a manifold of dimension n to the power n, then this will be less than Cn times the n-dimensional volume of n. So, and with one topological assumption, which is a bit complicated, so I won't state it precisely, but I will give example. So if Mn is what is called essential. So if you look at manifolds like S1 times round sphere, for instance, you can see that you need some control of the topology. Basically, there need to be enough topology in dimension 1, more or less. And so this is what, roughly, this is what this essentialness tells. For instance, this is okay for torize, real projective space, and also hyperbolic manifolds, and so connected sum of those. Okay, so this is what's known about one-dimensional systoles. So let's now get to higher systoles. So the definition is quite easy. For simplicity reason, and because that's where the proof usually works, we'll work with an homological version of the systole, whereas our first version in dimension 1 was tied to homotopy. So the definition is the following. So the K-systole of a Riemannian manifold Mng is equal to the infimum over all submanifold of dimension k, which are not zero in hk of m, of the k-dimensional volume of sigma k. So the definition is intuitive and promising, but there's one problem, is that usually it's very hard to control those systoles, and one cannot accept to have such good results as we have for the one systole. Namely, there is, in the case of interest to us, this was noticed before in higher dimensions by Gromov, But if we look at, so there is a theorem by Katz and Susio, which says that there exists metrics, a sequence of metrics on the manifold S2 times S2 such that so if I take the following quantity, so this is the 2 systole of S2 times S2 squared over the 4-dimensional volume of S2, so with this metric Gi, of course, of S2 times S2, then this go to plus infinity as I go to infinity. So we can find metrics of fixed volume, but whose systole is as big as we want. So that means that there is a sequence of metric of, say, volume 1 on S2 times S2, but such that any non-topologically trivial S2 inside this metric has a big volume. And if we change the metric, we can make this area of this S2 as big as we would want, while keeping the 4-dimensional volume fixed. So what would be a way out of this problem? There is one way which we won't explore here, but which I mentioned because it's of interest. So this is the study of the so-called stable systole. Which are a more refined invariant, which actually handles multiplicity better. And there is a... So this is a whole story. So, which was... Yeah, maybe let's quote Gromov. And another way out is to add curvature restrictions. So, and this is what we will do in this talk. So, let's now talk about positive scalar curvature. So if you think about positive Ricci curvature, what that gives us, so think of Meyer's theorem maybe, or Milnor's theorem in non-negative Ricci curvature, is some kind of metric smallness, or you could think about Bishop-Gromov too. And also some kind of topological simplicity. And we get both. So if you think about positive Ricci curvature, then Meyer's theorem will tell you at the same time that the diameter is bounded and that the fundamental group is finite. While in non-negative Ricci curvature, like the Bishop-Gromov inequality will give you some kind of polynomial growth, which is some kind of metric smallness. And using the usual argument of Milnor, that will give you that, at least if you're on something compact, then the fundamental group has polynomial growth, which is some kind of measure of topological simplicity. This cannot really be true for scalar curvature, because you can have manifold with pretty complicated topology which have positive scalar curvature. For instance, you can take connected sum, and since you can take connected sums of, say, length spaces or projective spaces or whatever, or products of sphere with the right dimensions, since you can take connected sum, you can also get pretty big metric invariants. Like, for instance, the diameter cannot be bounded by the scalar curvature. But actually, the more I study this topic of positive scalar curvature, and I will put quotes everywhere here, the more I'm under the impression that positive scalar curvature cannot give you topological simplicity and topological smallness, or simplicity, but it will give you either metric smallness or some simplicity on the topology. And this will be with big quotes, because this will be in a very, very weak sense. So topological smallness, we know, and in fact there are some universal things here, that when the topology is too complicated, for instance on the torus or on hyperbolic manifold, there are no metric of positive scalar curvature. And what this says is that if we know that there is some complexity in the topology, and that we still have positive scalar curvature, that will imply some smallness in some metric invariants. So let's give a first example of this, which is in dimension 3, which is a first non-trivial example. So this is a result of Bray, Brandler, and Neves. And I state it in the following way. It's not exactly the way they state it, but it works for us. So if three manifold has scalar curvature greater than 2 and second homology group non-zero, then the two systole of that 3 manifold is at most 4 pi. And moreover, they characterize the equality case by, so S2 times R, universal cover is S2 times R with the product metric. Okay, so this is the first step in dimension 3. Now, let's go to higher dimension and see what we can do. And I will jump straight to the case of S2 times S2. So we will be, so as the title of the talk implies, we will be mainly concerned with the two systole of positive scalar curvature metric on S2 times S2. And I will choose the normalization that the scalar curvature is greater than 4, which is what you get when you take two spheres of radius 1. So let's see what's going on if you take product of round metrics. So the condition, so here S2 of kappa 1 will be S2 with a metric of constant curvature kappa 1, and our condition on the scalar curvature will be that kappa 1 plus kappa 2 is greater than 2. So in that case, the 2 systole is exactly the volume of the smallest of the two factors, which you can write here in this form. So it's 4 pi over the maximum of kappa 1 and kappa 2. Okay, so what can we say? So we can say two things. So first, this is less than 4 pi, which is a good thing, and also there is some kind of relation. So if you think of so thanks to our inequalities on the curvature, so if you want to make the systole big, you should make one of the factors big. But if you make one of the factors really big, which would, for instance, entail to making K2 very small, to have the second factor very big, then you will need to make the first factor smaller to ensure this inequality. And so this is implied. So you can see that in the following way, like when kappa 2 go to 0, this goes to 2 pi. And it will be realized. It will be realized by a sphere in the first factor. So we see there is some interplay between the size of both factors here. Okay, so and that if you try to make one factor very big, you will make the other factor smaller, or at least of a control size. So for this, I will need to define some metric invariants that will quantify that thing, and I will phrase them in terms of this SL. So what is it? It's just the set of smooth surfaces inside the homology class of the first factor. So this is all the way you can have a surface which is homology equivalent to the first factor of S2 times S2. And given G, a Riemannian metric on S2 times S2, I will define what I call the left stretch, which will in some way control the size of the right factor. And this will be defined in that way. So that will be the supremum over all couples of surfaces in SL of the distance with respect to G between sigma 1 and sigma 2. So I take two surfaces inside the homology class of the first factor, and I try to make them as far apart as possible. So which would amount to like stretch the manifold as much as one wants. So the left systole now is just a restriction of the systole. So that will be the infimum of the area of the two-dimensional volume of sigma. But instead of looking at all non-homologically trivial surfaces, we look only at surfaces which are homologous to the first factor. So okay, maybe let's give a picture. So assume we have something which looks like a warp product. So this would be the second factor downstairs. And above that, we would have various spheres. And so the left stretch would be the distance between, actually, if it's really a warp product over this red sphere, it would actually be the diameter of the sphere. And okay, we'll put one smaller one, and the two systole, the left systole, sorry, would be the area of the smallest sphere that you can find among the green spheres in a loose way, like you are allowed to deform them in a homologically trivial way. So, and once I have these metric invariants, so I can give you what the theorem says. Okay. So this is the following. So assume S2 times S2 with a Riemannian metric G has, so first, scalar curvature greater than 4 and left stretch bigger than square root of 3 over 2 times pi. Then the left systole of G will be controlled by the following constant: 8 pi s squared over 4s squared minus 3 pi squared. And yeah, s is equal to the left stretch. So, okay, if we look at this is not that great, especially because we have an extra hypothesis, this hypothesis on the stretch. But if we look at that one, it's actually not bad, because when s gets bigger, which we would have in that situation when the second factor goes to infinity, then this actually goes to 2 pi. So in the regime where the right factor gets bigger and bigger and bigger, this inequality gets sharper and sharper. This is not the precise asymptotics that we would expect, but nonetheless, it's not too bad when the stretch is very big. And what does that say? Well, that says that if we have two spheres which are very far away from each other inside this left homology class, then we can find a small sphere, or a sphere of control size here. So in a way, this gives some kind of control on metric invariance of S2 times S2, because you could phrase it that way. So if you have a metric of positive scalar curvature on S2 times S2, then either its left stretch is small or its left systole is small. So there is some kind of balance between the two. And if you consider only the left systole, looking again at product, you need to have that kind of restrictions. You cannot get a universal bound on the left systole. Okay, so now we will give some metric inequalities in positive scalar curvature that we will use to prove the stretch systole inequality that I presented before. So first we will give a theorem by Zhu, by Jin-Tian Zhu, so which was put on the archive last year and published a couple of months ago. So it says the following. So assume our dimension, which we will denote by n plus 2 for obvious reason afterwards, is between 3 and 7, and assume also that we have some positive scalar curvature metric on S2 times Tn and with some normalization. I will assume that it's bigger than what you get when you take the round metric of radius 1 times the flat torus. So it's bigger than 2. Then the two systole of G is at most 4 pi, and moreover it's realized by a surface sigma which is homologous to this S2 factor. Okay, so how can we go and prove such things? So if you see the restriction here on the dimension, like this n plus 2 less than 7, so that screams that we are going to use minimal surfaces. So the trick here is to use what Gromov called Fisher-Colby chain symmetrization, which is a trick that was used already in Gromov-Lawson, where it is attributed to Fisher, Colby, and Chain, and also in Shane-Yao, like in the beginning of or middle of the 80s. So the thing is the following. So consider here some hypersurface. So this one. So, and let's assume that it is, so here in black we have S2 times Tn, and we assume that it is S2 times Tn minus 1 here, this blue surface. And then inside its homology class, we can find a new surface, maybe a little bumpy, but thanks to the dimension restriction, it will be smooth, which I will call sigma. So which will be homologous to S2 times Tn, and which will be area minimizing inside its homology class. So in particular, and it is all that we will need, this will be a stable minimal surface. Then, if we look at the second variation formula for area here, so already in Shane and Yao, you see that this will give you that sigma admits a metric of positive scalar curvature. However, so using a conformal deformation of the induced metric. However, this has two drawbacks. First, it doesn't really remember what the original metric on S2 times n was. And second, it doesn't even remember that the scalar curvature was greater than 2 to begin with. So instead, we will do something else. We will take sigma Okay, so this is sigma with the induced metric from its embedding in S2 times Tn. And we will make a word product with S1. And so I'm being pretty vague, and this is where the second variation enters. The length of the circle that we put on top of it will be governed with the right power by the first eigenfunction of the second variation operator. And then there is a, if you take a word product of this kind, then you will get that this has scalar curvature greater than 2. So we are able to preserve our lower bound on the scalar curvature that we had to begin with. And using this trick, then you can, so you need to be more careful than that. You need to use, and actually I stated the theorem of Zhu in a way which was convenient for me, but it is not really what is proved. Basically, what would be great would be that sigma would be S2 times Tn minus 1, but you cannot get that because it's only homologous to S2 times Tn minus 1. So you need to work with non-zero degree map. But let's cheat a little bit. And let's assume that sigma is S2 times Tn minus 1. Then I get a new metric on S2 times Tn here, which has symmetry here. Because here, if you think about it, this is actually a metric on S2 times R that you have quotiented. And then by Z to get sigma times S1. But it has symmetry in that factor. And then you can hit all the toric factors here, all the S1 factors, one after another, to have some surface, sigma twiddle, times a torus, and with some kind of word product matrix, but not really word product, but fibered, where above the surface, all fibers are flat tori in a controlled way, and there it's just Gauss-Bonnet that proves the theorem on the S2. And moreover, since this guy was already sitting here, well, and you continue, you get some other hypersurface inside that. So everything that happens inside those guys that you get here happens also in the original metric. And so this is how the Fisher-Culbertson symmetrization works, and this is proved. This is used to prove the theorem by Zhu. So now let's move to the result by Gromov. So, and first, an impossible challenge by Gromov would be to build a metric with positive scalar curvature, let's say greater than that of the sphere, on the torus. So we know that it's not possible since at least Shane and Yao and then Gromov and Lausanne. But let's try anyway. And let's make the stupidest of assumptions. So let's look for a metric of the form. So let's say dt squared plus phi of t squared dx squared on an interval times the flat torus. And let's try to make it with scalar curvature greater than n minus 1. Okay, and so what will happen will be the following. So there is no curvature in the direction of Tn. So if you want to get curvature here, you will have to bend. And if you bend in this direction, you will never be able to close this metric. You will need to get something like a critical point of phi on both sides to be able to close the metric. And before you reach that, you will run into some singularity. And when you run onto that singularity, you will find that the length you've put here will be 2 pi over n. Actually, I can even write for you what the function you get, if you try to have exactly n minus 1 scalar curvature. And so this will be with phi t equal to cosine nt over 2. That's it, yeah. To the power 2 over n. Okay, and actually, in using the Fisher-Colboy chain, but in a setting with boundaries, which makes things a little bit trickier, Gromov proved the following. So assume that we have a Riemannian metric on the product of an interval times the torus, so Riemannian metric G, so non-complete, if you're on the open, or it's a Riemannian metric with boundary, doesn't really matter, with scalar curvature greater than n minus 1. And set, so partial minus m to be minus 1 times tn minus 1. So you have two boundary components, one at minus 1 and one at 1, which I'll call partial plus and partial minus m. Then we have the following metric inequality. The distance between those two boundary components is at most 2 pi over n. So which is, and the inequality is optimal because of this explicit example. And Gromov in his IHES lectures gave two proofs of that. One was based on the Fisher-Colboy chain symmetrization. The thing was to, basically you were looking at area minimizer here, which would be like Tn minus 2 times an interval, and you would vary them like that. And using this symmetrization trick, you would gain one symmetry in this direction. However, this was very tailored to the fact that we have the topology of the torus to help us to make each step of this symmetrization work. So in his IHES lectures, Gromov proposed a new proof, which is based on a new thing which he calls the mu area. So this is a new functional. Instead of using the area functional, you will twist it with some density, which is integrated like, instead of you looking at the functional on hypersurfaces, you look at it on domains, and there is one part of the functional which is the integral of some weight function on the domain, and the other part is just the area of the boundary. So you still have an area, but you have a correction. And what this correction does is that it makes this middle torus here a stable guy and a minimum of this functional. So this enables us to not to worry too much about the boundary, to minimize things really inside the manifold and not have to worry about the boundary. And this gives the following results actually, which implies the first. So let's take Mn G with assume that the boundary of M has two boundary components which are disjoint. Assume also two things. So first we will assume that we are in the case where this width, Gromov called this some kind of width, is assumed. So the distance, so this bound is achieved, is equal to 2 pi over n. But the scalar curvature is too big, bigger than what we have here. So it's greater than n minus 1 plus delta. Then so there exists some hypersurface sigma n minus 1 which will be homologous to one of the boundary components, and such that sigma n minus 1 times S1, when you build, basically you look at the second variation of this mu area functional, and you build a warp product metric as we did in the usual Fisher-Colbretian symmetrization. And so this new metric has scalar curvature greater than delta. So basically what this tells us is that if you can stretch the two boundary components of M as much as in this boundary case for tori, and maintain a scalar curvature bigger than n minus 1, then you can actually fold your manifold back on itself, more or less, and retaining all the excess scalar curvature that you had to begin with. So this will be useful. Okay, so now with these two pieces, like the result by Zhu and the result by Gromov, we will be able to prove our stretch systole inequality. Okay, so now we are ready to prove the stretch systole inequality. So I won't do the quantitative version, but it is easy here to show you why this qualitatively why this must be true. So basically the result we want to prove is that if we have a positive scalar curvature metric on S2 times S2, and if we can find two surfaces inside the homology class of the first factor which are far away from each other, then we should be able to find another sphere which has, inside this homology class, which has small area. So, how will we proceed? So, we assume that the left stretch here is very big. So what does that mean? That means that we can find two S2s. I make them green because they will be inside the homology class of the first factor, and I can assume that they are far away. So the distance between those is of the order of the left stretch, which I assume is very big. Now what I can do is I can remove some small tubular neighborhoods of those spheres, and like we can assume that this would be like so let's assume for simplicity that this is really S2 times a point. So you need to do some topology to show that it also works in the case where it has higher genus, for instance. But let's assume that there are two surfaces here. Oh, I didn't give them names. So sigma 1 and sigma 2. And so I have tubular neighborhoods here, sigma 1 epsilon and sigma 2 epsilon. Sigma 2 epsilon, anyway. Epsilon. So if we have that, then what's going on? So the boundary of these tubular neighborhoods here, so it would be something like, so the tubular neighborhood inside would be something like S2 times a small disk, where the disk sits inside the red S2. And here it's the same thing. And if we take small enough tubular neighborhoods, we can assume that those are disjoint. So then, when we remove that, what we get here is something which looks like, which is actually with our simplifying assumptions. Otherwise, you need to use like non-zero degree maps. So this will look like S2 times S1 times an interval. Okay, so now if the stretch is big enough, we can use the theorem of Gromov, and that will tell you the following. That will tell you that you can find something here. Let's call that sigma 3, which looks like more or less S2 times S1. Basically, it will have a non-zero degree map to S2 times S1. And by the last theorem of Gromov that we said, so sigma 3 times S1 will have, for some word product metric, symmetric metric, scalar curvature greater than some delta which depends on the stretch. But then, since sigma 3 is S2 times S1, then this is actually S2 times T2. So here this will be by the theorem of Gromov. And so by the theorem of Zhu, we will have a control system. And it will come from this factor, which is ultimately this one. Okay, and this ends the proof of the theorem. So once you have both, it's very easy. What I hid here is that, okay, sigmas may be more complicated than just S2 times a point. So you have to make a little bit of topology to show that basically what you get is not necessarily that simple, but you have a non-zero degree map to that guy. And that does the trick. So finally, I will give some open question in that topic. So first, in the case of S2 times S2, still with scalar curvature greater than 4. So well, the question I'm interested in and I would like to answer is the following. So is the 2 systole less than 4 pi? So some clues why it may hold. Well, there is the case of S2 times T2, which was handled by Zhu. You can look at the following. So if G is a warped product of round S2s, then this is okay. Basically, what's going on is that the condition of the scalar curvature gives you a differential inequality on the warping factor, and the maximum principle will tell you that this warping factor needs to be small somewhere, so that there is a small two-sphere somewhere. So that will give you the answer. Okay, so and this is true also if the right stretch or the left stretch are not too small. So this is basically a corollary of what I said. So basically, if you assume that the left stretch is bigger than square root of 3/2 times pi, not sure that's very important, then you will get that the left systole or the right systole is at most 4 pi. Okay. So that would be something. So another natural question would be, can we get something can we improve things if we have like sigma 2 times S2, where this is a hyperbolic surface? So that would we would have like an inequality thanks to Zhu, but maybe we can take advantage of the hyperbolic geometry here to get something better. And then what is vastly open is like higher dimensions, and maybe false, but we like counterexamples too. Like Sk times Sl. So let's say K plus L greater than 5, and even like S3 times S1. I'm not sure we can control the 3 systole in that case. It's at least for me, it's an open question. So let me end this with some references. So first, there's the IHES lectures by Gromov, 4 lectures on scalar curvature, where you will learn about a lot of things, but where I learned about the mu area and the Fisher-Colbrey chain symmetrization. Then you have the article by Jintian Zhu, where he treats the case of S2 times the torus, which I built on. Now, some more general stuff. So if you want to learn about systoles, I give you 2 old surveys, but which I find very interesting, and which cover everything that I've mentioned so far. So one is in French by Berger, which is called Systole et applications selon Gromov. And so Berger himself say it's a companion survey to this other survey by Gromov, which is systoles and intersystolic inequalities. Thank you very much. I hope you've enjoyed this talk, and I will stay in touch for questions. Thank you.